So 1.2, take the quiz at 1.1, quiz 1.1 will start at 10:30. Next Tuesday, 1.3 and 1.4. Next Tuesday, there'll be a quiz on 1.2, but it's going to be on Pearson. You're going to get 2 attempts. Your best score will be kept. Today, what's going to post is a quiz prep for 1.2 on Pearson, so you can see how the quizzes are different than the homework. You cannot work. So if you're on question 3, you cannot go back to question 2. So I'm going to walk you through that. You get 5 attempts at the quiz prep. This is not taking the quiz. Doing this 5 times doesn't mean it's going to count for anything except practice. You got to do this. If you're happy with your first attempt, you don't need to do it twice. If you're not happy with your first attempt, then you need to do the second one. It will tell you your score after you finish the first attempt. Okay? And then by next Thursday, our goal is to be finished with chapter 1. You'll get a review for the test, and that's where we'll start getting to when the test is going to be. And I'm predicting that it should be the Thursday after we come back from Thursday after the drop date. Basically, that Thursday before Labor Day. So you wouldn't have to worry about anything during Labor Day. Made it focus. I have the wrong glasses on. I know you guys don't know the reference, but there was a show in the 70s called Sanford and Son. He was a junk dealer, older guy. And he would open up whenever he needed to read something, he'd pull open his drawer, and there was about 50 pairs of glasses in there, and he would pull out one until he could actually read. Keep on trying. It was a running gap on that. You could not put that show on the air these days. Okay, base 4. So if I were you, when you're going to convert this, we have 1, 2, 3, 4, 5 digits, 5 place time. So I'm going to write out these 5 little place time. This is the ones. This is the 4th place. What place is this? It's the 16th place. It's the 16th. This is the 1 because that's 4 to the 0. This is 4 to the 1st. This is 4 squared. This would be what place? The 64th because that's the 4 to the 3rd place. And this would be 256 because that's 4 to the 4th place. When you're dealing with base 10, here's 3 digits. Oops, that's not 3 digits. This one is the 1. That's the 10s. That's the 100s. This is 10 to the 0, 10 to the 1st, and 10 to the 2nd. So you go from right to left as you lay out those place numbers. The 1s is always your 0 power. So we have 1. Right here, we have a 2 times a 4. This is the 4th place. So that's going to be a 2 times a 4 when we do our conversion. In the 16th place, we have a 3. So to convert it into base 10, that's going to be a 3 times 16. 3 times 4 squared. In the 64th place, which is nice, we have a 0. So that's going to be a 0 times 64. And I'm writing it to make sure I have everybody accounted for. Doesn't hurt. It's going to happen. And here in the 256th place, the 4th place, we have a 3. 3 times 256. 3 times 4 to the fourth. The 4 to the fourth place, 4 to the third, 4 to the second, 4 to the first, 4 to the 0. So now we add up those values. The 3 times, the 256, the 0 times 64, 3 times 16, plus 2 times the 4, plus the 1. So that is 788, correct? 68, that's right, 750 and then 87. I was about 775. So 768, and then 0, and then a 48, then 8, and then 1. So we have, let's do this first. This is a 56, 57, and this is 768. And so we're going to get a 15 carry to 1, we're going to get 11 and 12, 2 carry to 1, we're going to get 825. Is that right? So this is 825, 810. Miss,
Where do we get all the rent and stuff?
are you down here?
Yes.
Oh. I wrote them down from those digit place values, those little lines, where I separated the numbers and put them in there. 4 to the 0, 4 to the first, 4 to the second, where I separated them into their individual place values. And then I rewrote it so you're going to do addition in between. Okay. Now we want to convert into base 5. This is where it gets a little more challenging. Over here, base 4, you can't have any of these digits bigger than a 3. If it's in base 4, it has to be a 3, 2, 1, or 0. Those are your only choices. If it's base 5, you can have a 0, 1, 2, 3, or 4. You can't have a 5. Just like when you're dealing with base 10, you cannot have a 10 as a digit. It goes 0 through 9. You have 9 to play with. You have 10 things to play with, but 10 isn't one of them. You have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are your only digits in base 10. You don't have one place value that actually is 10, the number 10. So it goes 0 to 9. So when I convert this into base 5, any of these digits would have to be 0, 1, 2, 3, or 4. So in base 5, let's think about this. I go from right to left. This is your 5 to the 0 or your ones place. This is 5 to the first or your 5 place. This is 5 to the second or your 25 place. This is going to be your 5 to the third or your 125 place. This is going to be your 5 to the fourth or your 625 place. And you can keep on going. You know when to stop when the number you're trying to convert, these won't go into it anymore. You want the biggest number that can divide evenly into the number you're trying to convert. 1 goes into it. Is there a bigger number? 5 goes into it. Is there a bigger number? Is there a bigger place size? 25 would go into that even, but is there a bigger base that would go into this? 125 would go into this. Is there a bigger base? The next base would be 625. Can 625 go into this easy? No. So you're not going to have the 625 place. You're going to have the 125. The 5 to the third. So we need to know how many 5 to the thirds are there. Right here, there were 3 of these 4 to the fourths, 3 of them. Well, I want to know how many 125s go into that 592. No, this doesn't go into the five, that whole number. 125 doesn't go to 59. So there's nothing in the hundreds place, there's nothing in the tenth place. So we go all the way over to the ones place. We know that 5 times 125 is 625 today. So it's probably going to be a 4. It will be a 4. Four times. I'm just doing a little long division. 4 times this is equal to 500. The remainder is 92. So this is 4 with a remainder of 92. So how many times we're going even in the 5 to the third place? In the 125 slot, you have a 4. So now we have a 92 remainder, and we use the 92 to figure out what's going to go here. Okay, 25 going to 92.
Yes.
Yep. So we're going to divide and see what we have. Divide by the next place size. How many times did 25 go into 92 even? 3 times. 3 times 25 is 75. Then we subtract. We're going to borrow. That's an 8. That's a 12. We get a 7. And we get a 2. Sorry, get a 1. So it goes in 3 times, remainder 17. In the 25 place size, it went in 3 times even. With a remainder of 17. And now you have that 17 left over. And we're now in the 5 to the first place. So we need to figure out how many times can that 5 to the first go into 17 even. How many times can 5, this place, go into the leftover even? 3 times. 3 times 5 is 15. And we subtract, you get what? You get 2. So it goes in 3 times evenly with a remainder of 2. So this is a 3, and our remainder is 2. So we're in the ones place. Can 5 go? Well, we're in the ones place. How many times is 1 going to 2? It goes into that. So 592 base 10 is equal to 4,000, not 4,000, 4,332 base 5. You know, if you made a mistake, if you're converting into base 5 and one of those digits is a 5 or 6 or 7 or 8 or 9, that wouldn't happen. You're not going to see that until test time. You'll see it on the homework for 1.1, but you're not going to see it until the test. I would definitely put something like that in the review sheet so you'll have something to practice. Okay. Left off, start. Start. 1.2. Decimals and negative numbers. Then we forget something. Turn around and say, yeah, questions. So yell something out if you have a question. Don't do it all. Page 10. Each time a digit moves to the left or right, the place value is multiplied by 10. If we go to the left, we're in the ones. Multiply by 10, we're in the 10. Multiply by 10, 10 times 10, we're in the 100 place. Multiply by 10, 10 times 100 is 1,000. You add a zero. Every time you multiply by 10, you add a zero. When you go to the left, you're multiplying by a 10 to a negative power. So if we're in the ones, which is 10 to the zero place. To get to the right side, you would multiply by 10 to the negative. So this is the 10, so that's 10 to the first. That's 10 to the second, or sorry, 100. That's 10 to the second. And over here, you got 1,000, 3 zeros, so 10 to the third. So when you go this way, the exponent is getting bigger. But if I go that way, look at the pattern, the exponents are decreasing one at a time. So when we get to the decimal, from 0, we subtract 1, we're at -1. So what the heck does that mean? A negative exponent means reciprocal. When you have a negative exponent, you're going to flip this base down to the denominator. You're dividing by 10. When you go to the right, you multiply by 10. When I go this way, I'm going to go, this is 1,000 divided by 10. That's how we get the 100. This 10, you take that 100, you divide by 10, and that's how you get that 10. To get the 1, you take that 10, divide by 10, and that's how you get this 1. When you go this way, multiply by 10, go that way, divide by 10. So when you hear the 1, you're going to go and divide by 10. So that divide by 10 compared with the exponent is the equivalence. Negative exponent. 1 over 10. 0.1. We move the decimal left to right. 1.0, move it one time this way, we get 10. Move it 2 times again, you get 100. Move it again, when you multiply by 10, that's where the 1,000 comes from. If I'm going that way, then I'm moving the decimal, so here's the 1. If I'm going that way and divide by 10, I'm moving it to the left. And that's why it's here now, and I get 0.1. If I divide by 10 again, because it would be 10 to the -2, I would move this again, and I would now have 0. There's a 0.1 on this side. The next one would be 0.001. 1,000. 10. How many zeros do you see? 3. -3. How many digits are to the right of the decimal? how many digits? 3, 10 to the negative 3. Okay. Since the decimal system has the same structure to the left and the right of the decimal, we can represent decimals with bundled objects. What you're looking at here is the equivalent of $2.56. So if we're going to do something different than what we did before in terms of drawing a picture, we have to supply a key. When you make a map, you need to supply a letter. You need to supply something that fixates or solidifies what an observer is trying to read.
Basically tell you what any symbol is on the map.
Right, to compare it to. What does it represent? So down here, if you don't put the key, we have no way of understanding what these little squares mean. So this key, when you put it here, each square, and it doesn't mean each green square, any square is worth a penny. Every square is worth a penny. So you have 6 scattered green little squares, or let's just say little squares. So since there's 6 of them, this would be 6 cents, 0.06. And then we group 10 at a time. We have another 10 little squares. So we now group 10 at a time, 10 pennies. And that's 0.10, 10 cents. And there's another 0.10, 10 cents. You got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's another one. And there's another one. And there's another one. And because remember, I didn't know what they were. Was it you guys that I told you about the big jar of money I have? Okay, so when you count a whole bunch of money, you count the penny, make, stacks together. So 10, 20, 30, 40, 50, that's 50 cents. And this is 6 cents. And in this little box right here, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the height. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's 10 across. So without trying to count every little square in there, 10 times 10, that means there's 100 little squares in there. There's 100 pennies in there. And how much money is 100 pennies? $1. So this is $1, and that's $1. So this represents a total of $2. So this is a picture of $2 plus 50 cents plus 6 cents. $2.56. Now, you're putting this to a child. You would take a little bit more time over it, and you might actually break out some pennies. Help them learn how to count. Help them learn how to group. Teach them not so much the value of money, but to teach them what dollars actually mean. And then you kick it up a notch and you could say, all right, we can replace this stack of 10 pennies with these other kinds of coins. We can replace a stack of 10 pennies with maybe 2 nickels or maybe just a dime. We can replace a stack of 6 pennies with a nickel and leave 1 penny. But that means you're doing one-on-one. It would be hard to teach this with a group of people, a group of students. Any questions? Base 10. working to the right of the decimal. Math is a language, pronunciation matters. When you take a language in the past, do they make you only speak that language in that class? No. I was a freshman in high school. I took French because the French teacher was my brother's roommate's girlfriend, Miss Beltram, or Madame Beltram. But actually back then, Matthew. Anyway, she was dating my brother's roommate, John Fry. They get married in the middle of the year. She becomes Madame Fry. Free. French fry. Never mind. So when we're in that class, we were only allowed to speak, no matter what it was. If we had a question, it had to be en français. That was always the retort. The answer. But we didn't speak French first. Even if we didn't know it, we had to try. And math was the same thing. Pronunciation. Learn how to speak the language. Learn how to understand when you speak the language, you got to pronunciate and enunciate clearly. Or else it doesn't filter through. Here's your decimal point. Out of the ones, you have ones and tens and hundreds, thousands, 10,000, 100,000, millions, 10 billion, 100 million, billions, 10 billion, 100 billion. Then you have trillion, trillions, 10 trillion, 100 trillion. What comes after trillions? Well, that would be when we get to the five. So between the fives and the threes, we have the trillion, quintillion, quadrillion. So after the trillion, you're quadrillion. Quadrillion, 10 quadrillion, 100 quadrillion, quintillion, 10 quintillion, 100 quintillion, hextillion for 6. Octillion for 8, septillion for 7, nontillion. Keep on going. You get really big numbers, you get numbers like a Google. The number Google is 10 to the 100. You get a number like a Googleplex, which is 10 to a Google. That's right. 10 to 100 is a Google, 10 to a Google is a Googleplex. Those are just huge numbers. That are never going to occur in elementary school. The elementary population. You know where they do occur? Googleplex? In the Simpsons. When they go to the movies, it's called Googleplex. Because the writers on the Simpsons, they graduated from Harvard, Princeton, Yale, and some of them have degrees in math. And they sprinkled math ever since that first year. That was our family time when we raised our kids. We'd all Sunday night sitting there for the TV, watching with them, and I'd be laughing more than the rest of the family because I understood all the math. Better bring up the kids' next. So now here's the deal. When you get to the decimal, on this side, the 1, there is no ones place on the right of the decimal. It goes from ones, it goes straight to the tenths. So that's one thing that is a little bit odd about the decimal on this side of the ones place. And then you have tenths, hundredths, thousandths. Tenths, 1/10, 1/10, a tenth, 1/100th, 1/100, a thousandth, so 1,000, a 10,000, so you have a 10,000 in the denominator. Each time you go one decimal over, you add another zero to the denominator. 100,000, 100,000, 10. So it's 0 point, there's one digit to the left, sorry, to the right of the decimal. One digit to the right. 100, there's 2 zeros. You have 2 digits, you have 0.01, 2 digits. Now you see how I put that 0 in front? When I write this, I put 0 and then 0.1, and 0.01. This one's going to be 0.001. 3 zeros on the 1,000. So 3 digits to the right. I'm not counting that first one. What place value is this first one? It's in the ones. So it's not part of the decimal. So I don't count it as part of the decimal. The reason why I put it is because students have crappy handwriting. When you don't put it, if the answer is 1,000, I will see this. And I can't tell if there's a decimal there or not, because it's written so lightly. If I have 5 thousandths, then this should be a 5. But if I have 5,025 over 1,000, then this would be 0.025. But if you don't really do a good job of that decimal, and I can't see it, can you guys see the little decimal I put on the back? Now can you see it? That's what I get from you guys is when I'm trying to grade stuff. I'm not kidding. I am not kidding. Why make it harder on me to grade your tests? I know I'm bitching about students that I've graded before, but you're going to do it to me again, Eddie. It's just Murphy's. So when you don't have a leading number, when you don't have something that runs, to make sure everybody understands what you're writing, you put a 0 in front. Then you begin your decimal. It's just a good habit. One of the things about doing better in math is create good habits, get rid of old habits. If what you're doing ain't working, fix it. Do something different. And if you need help, come here for me. On ones, we learned how to write the expanded form of the natural number. Are these decimals natural? No, they are not natural numbers because they're decimals. Natural numbers are just 1, 2, 3, 4, 5. The expanded form of a number is when a number is written so you can compose it in base 10. So how do you write 0.1 as a power of 10? This is 1/10, which is a power of 10, 10 to the negative 1. (0.01). That's 1 divided by 100. So that's 1/10 to the second power. So you're dividing by 10 to the second, so I have a power of 10, 10 to the negative 2. So if I had, I'm not going to do that one, I'm going to do 0.00001. So that is equal to 1 over what number, power, what number is here? Divided by 1 is 100, 1,000 is a million. What is it?
1,000.
What is it?
100,000.
100,000? Tens, hundreds, thousands, 10,000, 100,000. 1 with 4 zeros. Is that enough? No, that's 10,000. Because remember, there's no ones place. There's no ones place when you start with the tens place. Tens, hundreds, thousands, 10,000, 100,000. So you would have 5 zeros down below. This is 1/10 to the 5th, which is 10 to the negative 1. Which means you can just do this. How many times does the decimal move? It used to be 1.0. How many times did it move from here to get this? It had to move 1, 2. It had to move 5 times to get it back. 1, 2, 3, 1, 2, 3, 4, 5. 0.153 is that number. It moves 4 or 5 times. Three, 4, 5 times to make 1.0 into that. Let's do this. We're supposed to expand this. You have 1,000. That's a plus 200. And then you have 50 cents. So 0.50. And then you have 8 cents. 0.08. That's 1 times 10 to the 1. 10 to the 1. 10 to the 3rd. And this is 2 times, that's 100. So if it's 2 times 100, it's 10 to the 2nd. This is going to be plus 5 times. What place is that 5 in? It's in the tenths. So it's 5 times 1/10. 5 times a tenth, which is a dime, 50 cents. So what power is a tenth? 10 to the negative 1. And then plus, that is 8 pennies. So it's 8 times 100. A penny is 100th of a dollar. So that's 8 times 10 to the negative 2. Expand it using powers of 10. We stop there. That's all we want. Expand the number. Then I get the zooms. Best thing about having dogs when they come home, they're so happy to see you. They just go nuts. Zoom over. Okay. Pretty good. Usually get migraines. You may not want to think too much about this next one. How many numbers are there on a number line? There's an infinite number of them. So there's an infinite number of numbers on a number. How many numbers are there that are negative? Just the negatives. There's an infinite number going on. How many infinite numbers are positive on just to the right? So there's an infinite number of numbers total on the number line, but then you have an infinite number of numbers going just to the left, but you also have an infinite number of numbers just going to the right. Wouldn't the infinite number of numbers that are positive be smaller than the infinite number of numbers that are all on the number line? Because it's only half of the number line. So like half of infinity. But what's half of infinity? So infinity. There are different sizes of infinity. There's different sizes of infinity. 1, 2, 3, 4, 5, 6. And then we zoom in to all the values between 4 and 5. So when we zoom in to all the numbers between 4 and 5, now let's slice it up into now we're zooming into just between the 4 and the 5. So this is 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, 4.7, 4.8, 4.9, and then 5. So we slice it up into tenths. It's like taking $4 to $5, and then you have all the dimes in between. But we can slice dimes up into pennies. So in between $4.20 and $4.30, we have pennies. So zoom in right here and do the slicing again. Just between the 4.2 and the 4.3. So that's what, so if this zoom in. Right here, this is 4.2. This is now 4.3. So there's 10 equal slices. You got 4.21, 4.22, 4.23, 4.24, 4.25, 4.26, 4.27, $4.28, $4.29, and then $4.30. The gas pump, they actually sell gas for $4.29 and then another 9 cents. 9/10 of a cent. 9/10 of a cent would be in the thousands, folks. So now you're taking a tenth of 100, so now you're in the thousands. That's where the tax comes in. So we're gonna zoom in right here. We're zooming in between 4.29 and 4.3. Technically, this is 4.30. So our last counting was to the nearest hundredth. Now we're counting to the nearest thousand. This is going to be what number? 4.291, 4.292, 4.293, 4.294, 4.295, 4.296, 4.297, 4.298, 4.299, 298, wow. 4.399, 4.300. How many times do you think we can zoom? An infinite number of zooms. Because now that's right here in between 4.299 to 4.300. And you get the picture. So, in the course of the history of mathematics, this is one of the methods that mathematicians would use to estimate answers. They would use something called intermediate value theorem, where if a graph or a value had a positive answer, and then in between two numbers, let's just say between 4.2 and 4.3, it changed the value of the value substitute changed from positive to negative. Then somewhere in this interval, the value changed and crossed zero. So there's a zero in between 4.2 and 4.3. So then they slice this up. Usually they sliced it right in the middle and they plugged in 4.25. And they kept slicing and slicing and slicing and trying numbers and numbers and numbers until they could zero in on a solution. Because that was the only way to solve something if they couldn't solve it with factoring or other methods. So intermediate value an approximation. They didn't have to distract them. But you can zoom in an infinite number of ways. A Greek mathematician started this about 300 BC. His name was Zeno of Elea. And he posed this question. Achilles and a tortoise have a race. The tortoise gets a head start. And in this race, Achilles can only get to 1/2 of the tortoise's position. So every time the tortoise moves, Achilles can only get to 1/2 of the tortoise's location. So if they start here, Achilles can only get to half the distance. So if the tortoise is here now, Achilles can only get to half of that distance. If the tortoise is here now, and Achilles is here, the Achilles can only get to half of that distance in between. Can only cut it in half. Put it into this scale. We cleaned it up a little bit. If this is you, and you are, let's say, 8 feet from a wall, and you are trying to get to the wall, but with each step, you can only go half of the distance. Now, technically, that makes sense Because if you're gonna walk from here to the wall, you will always cross the halfway point. If I'm gonna go from here to that wall, I'm always gonna cross the halfway point sometime. So if I have to stop at the halfway mark every single time, can I ever reach the wall? No. If I have to stop at the halfway mark every single time with each step, I will never reach the wall. Because if I go from here to here and I can only go halfway, my first step would be at 4 feet. My next step would be at 1/2 the distance, it would be at 2 feet, and now I'm here. Then I can do one more step and I'm at 1 foot. And then I take another step and now right here at 1/2 a foot. And then I can take another step and now I'm at 1/4 of a foot. And then I can take another step, half of 1/4, and at 1/8 of a foot. If I take another step, halfway would be 1/16. Half of that would be 1/32. Half of that would be 1/64. 1/128. 1/256. 1/512. 1/1024. 1/2048. I'm never going to get to 0. On a number line, infinite number of numbers. To the left, negatives, infinite number of negatives. To the right, positive, infinite number of positives. The number of positive numbers, the infinity, is a smaller set of infinity than the whole set of numbers. Between 0 and 1, there are an infinite number of numbers. There's an infinite number of numbers between 0 and 1. And that's a smaller set of infinity than the infinite number of numbers between 0 and 2, which is a smaller set of infinity between 0 and 10, which is smaller than the whole thing. Infinity comes in many sizes. What do you think infinity plus infinity? Infinity. You have an infinite number of objects, and add more, another infinite number of objects, you get an infinity number. Okay, ready for the mic. What do you think infinity minus infinity?
No.
It would be nice if it was 0, but that answer is indeterminate. Which is a mathematical way of saying, oh, there's different sizes of infinity. The infinite number of numbers minus the infinite number of numbers there, one's bigger, one's smaller, you're not going to get 0. Sometimes the answer is 7. That's the level of we do in calculus. When we get something that's indeterminate, we got algebra, so we can actually do the subtraction problem, one infinite minus another. You're not going to teach elementary school or intermediate school kids calculus. But there's stuff beyond. When I was a student taking false classes, I would come out of a calculus class and I go, there cannot be anything more difficult than what I just left. Every time you are trying to find the math mountain, and you reach to the top, well, you know that that's just a hill that you can't see, that there's a bigger hill behind it because you're just staring at this top, but it's hiding the bigger hill here. But then there's another hill above that one that you can't see because all you can do is see that one. But you think you're getting to the top of everything you could possibly, it's hiding another one behind me. But that's okay. It's like, do you know a doctor that specializes in everything? Brain surgery, cardiac surgery, neurological? No. You know, people that specialize in feet. That's all they do. I'm just doing feet. Give me the feet. That's their special. And thank goodness we do. There are mathematicians that just specialize in algebra. You know, well, how do you do that? Well, there's so much more behind algebra that I know I've never been exposed to. Okay. We're not ready to do that quiz prep. Obviously, we don't have enough time to do it. So we'll leave that, and I'm going to move the date for the 1.2. This will be available on the, we'll do that with 27. And this will be due. Okay. If I just, would it be better for you to have the due date right away, just that day, so you don't have to worry about, oh shoot, I got to get this done on over the weekend, or just make sure the due date is like Thursday night? Because I'll do whatever you want. Tell you what, think about it. Because I have given due dates like, here it is, it's available on Thursday. You have until Sunday night to get it done. Sunday night rolls around, oh, I forgot. Or even Monday night, that's classic too. And it's still, oh, I forgot. If I do. So I'll ask that question next Tuesday. So this will post next Tuesday. We'll walk through the quiz. So right now it's time to do your actual in-class quiz on cardinality. And I do know that I am right now, I've been all over the place. I'm going to question you before you do it. Do you have any questions? What the heck is going on? I'm not going to assume that you have understood everything I've been talking about. What do they have to do now? Ask them. Turn your brain back to the beginning of cardinality. How many terms are in the set?
The one where it's like the little sign, the alligator, and then the other one under it means.
So greater than or equal to, so you actually include that number.
Okay.
Okay. When you're done, just bring it on up, turn it in, and have a nice weekend. You don't have to stick around. Yes. Please put your first and last name legibly. And yes, it is open note. These are open note. You can have anything you want out. What do you know if you like to talk to the group? Nobody really want to say. Welcome. Read. Set notation.